Subscribe to the channel so you don't miss out on any of these videos. The universe is not just vast, it's filled with secrets, so perplexing that even our most brilliant minds are left with more questions than answers. But among all the wonders that surround us, there's something particularly mind-boggling, a category of things that, quite frankly, shouldn't even exist according to what we think we know about reality. I'm talking about exotic matter. These are strange and unknown forms of matter predicted by theoretical physics. Imagine materials so bizarre, so counterintuitive, that they challenge the very fabric of our understanding of the cosmos. What if these things are not just theoretical ideas, but are out there, shaping the universe and holding the keys to revolutionary technologies of the future? That's what we're diving into today. Exotic matter is not like the regular matter that makes up everything we see, touch, or interact with. It's a term used for theoretical substances that don't follow the same rules as ordinary matter. And when I say ordinary matter, I mean the stuff you're familiar with: protons, neutrons, and electrons. Exotic matter goes way beyond that. Some of it could be hiding in plain sight, while other types might exist only under extreme conditions in the most hostile corners of the cosmos. But here's the kicker: exotic matter isn't just strange for the sake of being strange. It could play a pivotal role in how the universe works, and it might even hold the answers to some of humanity's biggest questions. Let's start with one of the most fascinating concepts: strange matter. Sounds ominous, right? Strange matter is a hypothetical substance made up of particles called strange quarks. To understand this, let's back up a little. Normal matter, like the stuff in your body or the air around you, is made of protons and neutrons. Those protons and neutrons are, in turn, made of smaller particles called quarks, up quarks and down quarks, to be specific. But in the realm of high-energy physics, other types of quarks can emerge, and one of these is the strange quark. Now, strange matter isn't just made up of a few strange quarks. It's theorized to be an ultra-dense form of matter where strange quarks dominate. Here's the scary part: some physicists speculate that if strange matter were to come into contact with regular matter, it could transform the regular matter into more strange matter, like some kind of cosmic contagion. Picture a single droplet of strange matter falling into a planet. It could theoretically convert the entire planet into strange matter. But before you lose sleep over that, keep in mind that this is all highly theoretical and hasn't been observed yet. Strange matter might exist in some of the most extreme environments in the universe, like the cores of neutron stars. Neutron stars themselves are already mind-blowing. They're the collapsed remnants of massive stars, with densities so high that a sugar cube-sized piece of one would weigh as much as a mountain. But inside these stars, the pressure and energy might be so intense that normal matter gets crushed into strange matter. If that's true, then strange matter could be one of the most stable forms of matter in the universe, potentially outlasting everything else. But that's just one flavor of exotic matter. Another mind-bending type is antimatter. If you've heard of antimatter, you probably associate it with science fiction, starships powered by antimatter engines, that kind of thing. But antimatter is very real, and it's every bit as strange as it sounds. To understand antimatter, think of it as the mirror image of regular matter. For every particle of matter, there's a corresponding antiparticle with the same mass but an opposite charge. For example, the antiparticle of an electron is a positron, which has a positive charge instead of a negative one. Here's where things get wild. When matter and antimatter meet, they annihilate each other in a burst of pure energy. This is not just a Hollywood trope, it's backed by solid physics. The energy released from this annihilation is immense, far greater than what you'd get from any chemical reaction, or even nuclear fission. If we could harness antimatter, it could revolutionize energy production and space travel. Just a few grams of antimatter could theoretically power a spaceship to Mars and back. But there's a catch: antimatter is incredibly rare in the universe. Scientists can create tiny amounts of it in particle accelerators, but producing it on a usable scale is still far beyond our capabilities. And then there's the big mystery: why is there so much more matter than antimatter in the universe? According to our current understanding, the Big Bang should have created equal amounts of matter and antimatter. Yet, here we are, in a universe dominated by matter. This imbalance, known as baryon asymmetry, is one of the biggest unsolved puzzles in physics. Some theories suggest that exotic matter like axions could hold the key to solving this mystery. Speaking of axions, these are another exotic type of particle that's purely theoretical at this point. Axions were first proposed to solve a problem in quantum physics related to the strong nuclear force, which is one of the fundamental forces that hold atomic nuclei together. But axions are intriguing for another reason. They could be a candidate for dark matter. Dark matter is the mysterious substance that makes up about 27% of the universe. We can't see it, touch it, or directly detect it, but we know it's there because of its gravitational effects on galaxies and other cosmic structures. If axions are indeed the particles that make up dark matter, it would be a groundbreaking discovery. These particles would be incredibly light and interact with regular matter so weakly that they'd be almost impossible to detect. But scientists are developing clever experiments to look for them, including the use of ultra-sensitive detectors and powerful magnetic fields. If we ever find axions, it could revolutionize our understanding of the universe and unlock new technologies we can't even imagine yet. One potential application of exotic matter lies in the realm of wormholes, theoretical shortcuts through space-time that could allow for faster-than-light travel. Wormholes are a staple of science fiction, but they're also a serious topic of discussion in theoretical physics. For a wormhole to stay open and stable, it would require a type of exotic matter with negative energy density. Negative energy sounds like something out of a fantasy novel, but it's a concept grounded in quantum mechanics. While we haven't discovered any materials with this property, the search continues, and exotic matter might just hold the key. Exotic matter also has implications for understanding black holes. Some theories suggest that the cores of black holes might contain forms of matter we've never encountered, compressed to densities beyond anything we can replicate on Earth. These conditions could give rise to entirely new states of matter, potentially revealing deeper insights into the nature of gravity and space-time. And then there's the tantalizing possibility of using exotic matter for advanced technologies here on Earth. Imagine materials that can conduct electricity with zero resistance at room temperature, or substances that can manipulate gravity itself. While these ideas might sound like science fiction, they're grounded in the kind of physics that exotic matter explores. The more we learn about exotic matter, the more it becomes clear that our current understanding of the universe is just the tip of the iceberg. Every discovery leads to new questions, and every question brings us closer to unlocking the ultimate secrets of existence. Exotic matter isn't just a curiosity, it's a window into the deeper workings of reality, a glimpse at what lies beyond the boundaries of what we know. If exotic matter pushes the limits of our understanding, it also redefines what's possible in the universe. As we continue exploring its potential, one thing becomes clear: these theoretical substances are not just footnotes in physics textbooks. They're central to some of the biggest mysteries and boldest ambitions of humanity. Let's keep unraveling their secrets. One of the most intriguing areas where exotic matter might come into play is time travel. Now, before we dive into this, let's make one thing clear: time travel, as depicted in movies, is still purely speculative. However, theoretical physics doesn't rule it out entirely. Certain solutions to Einstein's equations of general relativity suggest that time loops, or closed time-like curves, could exist under specific conditions. These solutions often rely on the presence of exotic matter with negative energy density. Without such a substance, these time loops would collapse almost instantly, rendering time travel impossible. But if we could somehow harness exotic matter, the door to manipulating time might just crack open. The idea of using exotic matter for time travel isn't as far-fetched as it might seem. Scientists studying quantum mechanics have already observed phenomena that appear to violate the classical understanding of cause and effect. These experiments hint at the possibility that our conventional view of time might not be entirely correct. Could exotic matter be the missing piece of the puzzle? While we're still far from turning this idea into reality, it's a tantalizing prospect that keeps physicists up at night. Moving from time travel to the structure of the universe itself, exotic matter might also help us understand cosmic inflation, the rapid expansion of the universe that occurred just after the Big Bang. During this phase, the universe grew exponentially in size in a fraction of a second. What drove this sudden expansion? Some theories propose the existence of a scalar field, a type of exotic matter that could have acted as a repulsive force, pushing the fabric of space-time outward. If we can confirm the existence of such a field, it would not only explain cosmic inflation but also provide insights into how the universe came to be. This leads us to another mind-bending concept, the multiverse. If exotic matter played a role in the birth of our universe, could it also be responsible for the creation of others? The idea of a multiverse suggests that our universe is just one of countless others, each with its own set of physical laws and constants. Some theories even suggest that strange matter or axions could serve as the seeds for these alternate universes. While the multiverse remains a highly speculative idea, it's one that exotic matter could help us explore, potentially answering the age-old question of whether we're truly alone in the grand scheme of existence. But let's not overlook the practical implications of exotic matter here on Earth. One of the most exciting possibilities is the development of quantum technologies. Exotic particles like axions could revolutionize quantum computing, making it faster, more efficient, and capable of solving problems that are currently impossible. For example, quantum computers could use exotic matter to simulate the behavior of other exotic forms of matter, accelerating our understanding of the universe. And then there's the potential for exotic matter to transform our understanding of gravity. Current theories, such as Einstein's general relativity, describe gravity as the curvature of space-time caused by mass and energy. But these theories break down when applied to extreme environments, like the interiors of black holes. Exotic matter might hold the key to developing a unified theory of gravity, one that bridges the gap between general relativity and quantum mechanics. Such a breakthrough would be nothing short of revolutionary, opening up new avenues for science and technology. Speaking of black holes, let's dive deeper into their relationship with exotic matter. Black holes are among the most extreme objects in the universe, with gravitational forces so strong that nothing, not even light, can escape. The event horizon of a black hole marks the point of no return, but what lies beyond it? Some theories suggest that black holes could harbor exotic states of matter, compressed to densities that defy comprehension. These states might provide clues about the nature of space-time itself, revealing whether it's possible to bridge the divide between the classical and quantum worlds. In fact, exotic matter might even play a role in what are known as white holes, the theoretical opposites of black holes. While black holes pull everything in, white holes are thought to expel matter and energy, potentially serving as cosmic fountains. Could exotic matter be the driving force behind these enigmatic objects? If so, it would add yet another layer of complexity to our understanding of the universe. And then there's the question of dark energy, the mysterious force responsible for the accelerated expansion of the universe. Like dark matter, dark energy remains one of the biggest enigmas in modern physics. Some scientists speculate that it could be a form of exotic matter, one that exerts negative pressure on space-time. If this theory is correct, then understanding exotic matter could help us unlock the secrets of dark energy, bringing us closer to a complete picture of the cosmos. But exotic matter isn't just about understanding the universe. It's also about pushing the boundaries of what's possible. Imagine a future where exotic matter is used to create materials with properties we can barely imagine today. Think of spacecraft that can manipulate gravity, buildings that can withstand any force, or energy systems that make fossil fuels and nuclear power obsolete. These might sound like the stuff of science fiction, but they're the kinds of possibilities that exotic matter could make real. At its core, the study of exotic matter challenges us to think beyond the limits of our current knowledge. It forces us to confront questions that have no easy answers and to explore ideas that defy common sense. But that's the beauty of science. It's not just about what we know, it's about what we're willing to discover. The universe is a place of infinite wonder, and exotic matter is one of its most tantalizing mysteries. From strange matter to antimatter, axions to dark energy, these substances push the boundaries of what we know and open up new horizons for exploration. Whether they hold the key to understanding the universe or unlocking the technologies of tomorrow, one thing is certain: Exotic matter is a field of study that promises to reshape our understanding of reality itself. As we continue our exploration of exotic matter, it becomes increasingly clear that this is not just a niche topic in theoretical physics. It's a cornerstone of some of the most profound questions about the universe and our place within it. Let's delve even deeper into the tantalizing implications and unsolved mysteries surrounding these extraordinary substances. One of the most fascinating potential applications of exotic matter lies in the concept of warp drives, a staple of science fiction but also a topic of serious scientific inquiry. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical model for faster-than-light travel that doesn't violate the known laws of physics. The idea is to compress spacetime in front of a spacecraft and expand it behind, effectively allowing the ship to surf through space without moving in the traditional sense. However, this concept requires the existence of negative energy, or exotic matter, to stabilize the warp bubble. Without exotic matter, the Alcubierre drive remains a fascinating but impractical theory. If we ever discover or create exotic matter in usable quantities, it could turn this dream into a reality, opening up the stars to human exploration. The role of exotic matter in wormholes, another staple of speculative science, cannot be overstated. Wormholes, or Einstein-Rosen bridges, are hypothetical tunnels that could connect distant points in spacetime. While general relativity allows for their existence in theory, keeping a wormhole stable long enough for travel would require exotic matter with negative energy density. This is because the intense gravitational forces at the wormhole's throat would otherwise cause it to collapse. If exotic matter can be harnessed, wormholes could revolutionize space travel, allowing us to traverse unimaginable distances instantaneously. However, the feasibility of such a feat remains a topic of intense debate among physicists. Beyond practical applications, exotic matter may also help us answer fundamental questions about the universe's origins and ultimate fate. Consider the concept of strange matter, a hypothetical substance composed of up, down, and strange quarks. Strange matter is thought to be incredibly dense and stable, possibly more so than ordinary nuclear matter. Some theories suggest that strange matter could exist at the cores of neutron stars, forming so-called strange stars. These exotic stars could provide critical insights into the behavior of matter under extreme conditions, helping us refine our understanding of the strong nuclear force, one of the four fundamental forces of nature. Strange matter also raises some unsettling possibilities. One speculative idea is that strange matter could be contagious, converting ordinary matter into more strange matter upon contact. While this is purely theoretical and highly unlikely to occur naturally, it's a chilling reminder of how little we truly understand about the universe. Could strange matter play a role in cosmic events we don't yet comprehend? Could it even be a factor in the universe's eventual fate? Let's not forget antimatter, one of the best-known exotic forms of matter. Antimatter is the mirror image of ordinary matter, with particles that have the same mass but opposite charges. When matter and antimatter meet, they annihilate each other, releasing vast amounts of energy. This annihilation process makes antimatter a potential candidate for advanced energy systems or even propulsion technologies. Imagine spacecraft powered by antimatter engines, capable of reaching distant planets and beyond. However, creating and storing antimatter remains a monumental challenge. Currently, we can only produce tiny amounts in particle accelerators, and the cost of generating even a gram of antimatter is astronomical. But if we ever overcome these hurdles, antimatter could become one of the most powerful energy sources known to humanity. The mysteries don't stop there. Exotic particles like axions and sterile neutrinos may hold the key to solving the enigma of dark matter, which makes up about 27% of the universe but has yet to be directly observed. Axions are hypothetical particles that are extremely light and interact very weakly with ordinary matter, making them difficult to detect. However, their unique properties make them a prime candidate for dark matter. Sterile neutrinos, another dark matter candidate, are even more elusive, interacting only through gravity and not through the electromagnetic or weak nuclear forces. Detecting these particles would not only confirm their existence but also shed light on the structure and evolution of the cosmos. the potential implications of exotic matter extend to the quantum realm as well. Quantum mechanics, the branch of physics that deals with the behavior of particles at microscopic scales, is rife with phenomena that defy common sense. Exotic matter could help us understand these phenomena and even harness them for practical use. For instance, quantum entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of the other, regardless of distance, could be better understood through the study of exotic particles. This understanding might pave the way for revolutionary technologies like quantum communication and quantum computing. Exotic matter also raises profound philosophical questions. What does it mean for something to exist? If exotic matter is so different from ordinary matter that it barely interacts with it, can we truly say it exists in the same way? These questions challenge our understanding of reality itself, forcing us to reconsider the boundaries between the known and the unknown. And then there's the question of how exotic matter fits into the larger cosmic puzzle. Could it be the missing link that ties together seemingly unrelated phenomena, from black holes to dark energy? Could it help us develop a unified theory of everything, reconciling the inconsistencies between general relativity and quantum mechanics? These are the kinds of questions that drive scientists to continue exploring this enigmatic field. Exotic matter is more than just a theoretical curiosity. It's a gateway to some of the most profound mysteries of existence. Whether it's unlocking the secrets of the universe's origins, enabling advanced technologies, or challenging our very understanding of reality, exotic matter holds the promise of transformative discoveries. As we continue to probe its mysteries, one thing is certain: the journey will be as thrilling as the destination. Exotic matter also holds the potential to redefine our understanding of cosmic balance. One of the most puzzling aspects of the universe is the apparent imbalance between matter and antimatter. According to theoretical models, the Big Bang should have produced equal amounts of both. However, our observable universe is overwhelmingly composed of matter, with antimatter existing only in trace amounts, or in artificially created environments. This asymmetry remains one of the biggest mysteries in physics. Some researchers speculate that exotic particles, like Axions or other forms of hypothetical matter, might hold the key to this imbalance. For instance, certain interactions involving these particles in the early universe could have led to a slight favoring of matter over antimatter. If confirmed, this would not only solve the antimatter puzzle but also provide critical insights into the mechanisms that shaped the universe shortly after the Big Bang. Another captivating possibility lies in the idea of topological defects. These are theoretical structures that could have formed during phase transitions in the early universe, when it cooled down from its incredibly hot and dense state. Exotic forms of matter, such as magnetic monopoles or cosmic strings, might exist as remnants of these transitions. Cosmic strings, for example, are hypothesized to be one-dimensional defects with immense mass and energy. If they exist, they could help explain the large-scale structure of the universe, including the distribution of galaxies and galaxy clusters. Magnetic monopoles, on the other hand, are hypothetical particles that carry a single magnetic charge, either north or south, unlike ordinary magnets, which always have both poles. Their existence would not only revolutionize our understanding of magnetism but also have profound implications for unified theories of physics. If discovered, magnetic monopoles could provide direct evidence of the grand unification theory, which aims to merge the electromagnetic, weak, and strong nuclear forces into a single framework. The concept of negative mass is another mind-bending topic in the realm of exotic matter. In classical physics, mass is always a positive quantity, corresponding to the amount of matter in an object. However, certain theoretical models suggest that negative mass could exist under specific conditions. An object with negative mass would behave in bizarre ways. For example, if you pushed it, it would accelerate toward you instead of away. Negative mass could theoretically interact with positive mass to create systems that defy conventional physics, such as perpetual motion or exotic propulsion mechanisms. The implications of negative mass extend to the study of dark energy, the mysterious force driving the accelerated expansion of the universe. Some scientists have proposed that dark energy might be linked to a field containing particles with negative mass. If true, This would not only solve the dark energy mystery but also open up entirely new avenues for exploring the universe's large-scale behavior. Let's shift our focus to quark matter, a theoretical substance that challenges our understanding of atomic structure. Ordinary matter, as we know it, is composed of atoms, which in turn are made up of protons, neutrons, and electrons. Protons and neutrons are themselves composed of quarks, bound together by the strong nuclear force. However, under extreme conditions, such as those found in the cores of neutron stars, quarks might break free from their confinement, forming a new state of matter known as quark-gluon plasma or strange quark matter. Quark-gluon plasma is believed to have existed only briefly after the Big Bang, providing a glimpse into the universe's infancy. Studying this exotic state of matter could help us understand the strong nuclear force in unprecedented detail. Strange quark matter, on the other hand, might be stable enough to persist in certain cosmic environments, potentially forming strange stars or even strangelets, hypothetical particles that could act as seeds for converting ordinary matter into strange matter. While purely speculative, the existence of strangelets could have profound implications for the stability of the universe. Exotic matter also plays a crucial role in the study of black holes, some of the most enigmatic objects in the universe. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. At their cores, known as singularities, the known laws of physics break down. Some theories suggest that exotic matter could exist within or around black holes, influencing their properties in unexpected ways. For example, the presence of exotic particles might stabilize certain types of black holes or even create new categories of compact objects, such as boson stars or gravastars. Boson stars are hypothetical celestial objects composed of bosons, particles that follow a different set of quantum rules than the fermions, making up ordinary matter. These stars could form under specific conditions involving exotic matter, offering an alternative explanation for some astrophysical phenomena currently attributed to black holes. Gravastars, on the other hand, are theoretical objects where a shell of exotic matter surrounds a region of spacetime altered by extreme gravitational effects. If gravastars exist, they could provide an alternative explanation for observations traditionally associated with black holes, challenging our understanding of these cosmic giants. The role of exotic matter extends to cosmology and the multiverse hypothesis. Some versions of string theory and other high-dimensional models propose that our universe is just one of many within a vast multiverse. Exotic matter could serve as a bridge or boundary between these parallel realities, offering a mechanism for their interaction. For example, brane world scenarios in string theory suggest that our universe is a three-dimensional brane embedded in a higher dimensional space. Exotic matter might exist in these extra dimensions, influencing our universe in subtle but measurable ways. The discovery of exotic matter could also revolutionize our understanding of time and causality. In certain models, exotic matter could make time travel possible by creating closed time-like curves, paths through spacetime that loop back on themselves. While this idea remains highly speculative and fraught with paradoxes, it underscores the profound implications that exotic matter could have for our understanding of reality. Ultimately, the study of exotic matter is not just about answering scientific questions, it's about pushing the boundaries of human knowledge and imagination. Each discovery in this field has the potential to redefine our understanding of the universe, challenge our preconceptions, and inspire new generations of scientists and thinkers. Exotic matter's implications for time travel and causality extend far beyond theoretical physics into realms that could alter the very fabric of our existence. One of the most tantalizing possibilities is the creation of wormholes, hypothetical shortcuts through spacetime that could connect distant points in the universe. For a wormhole to remain stable and traversable, it would require a material with negative energy density, often associated with exotic matter. This negative energy could prevent the wormholes, mouths, from collapsing under immense gravitational forces, potentially allowing safe passage through the cosmic tunnel. The concept of wormholes aligns with solutions to Einstein's general relativity equations. However, the practical realization of such a structure remains speculative due to the unconfirmed existence of exotic matter with the required properties. If future technologies could harness such matter, it might not only enable interstellar travel but also allow humanity to explore the farthest reaches of the universe in ways once relegated to science fiction. The role of exotic matter in wormholes isn't limited to transportation. It also brings up profound questions about paradoxes and the nature of time. For example, if one end of a wormhole moves at relativistic speeds while the other remains stationary, a time difference could arise between the two ends, creating a potential time machine. This leads to the infamous grandfather paradox, where changes to the past might affect the future in unpredictable ways. While such paradoxes remain unresolved, they highlight how exotic matter could blur the boundaries between science and philosophy. Beyond wormholes, exotic matter could also be key to unlocking the mysteries of quantum gravity, the elusive theory that seeks to unify quantum mechanics and general relativity. Current models of quantum gravity, such as loop quantum gravity and string theory, often predict the existence of exotic particles or states of matter that challenge our classical understanding of space and time. For instance, in some models, exotic matter might interact with spacetime in ways that reveal the quantum nature of gravity, shedding light on phenomena like black hole evaporation and the origins of the universe. In the realm of cosmic inflation, exotic matter could play a central role in explaining how the universe expanded exponentially in its earliest moments. Theoretical particles like inflatons, fields associated with the rapid expansion, are considered exotic due to their unique properties. Understanding these fields could solve fundamental puzzles about the universe's uniformity, large-scale structure, and the seeds of galaxy formation. If exotic matter is indeed linked to inflation, it could provide a window into the universe's first fractions of a second, where the laws of physics as we know them may have been drastically different. Exotic matter is not just about understanding the past. It could redefine our future, particularly in the context of energy generation and storage. Consider the potential of antimatter as an energy source. When matter and antimatter annihilate, they release energy with 100% efficiency, far exceeding the capabilities of chemical or even nuclear reactions. This makes antimatter an ideal candidate for powering spacecraft, enabling journeys to other planets or even star systems. However, producing and storing antimatter remains a significant challenge due to its tendency to annihilate upon contact with ordinary matter. Another intriguing prospect is the use of axions or other exotic particles to create advanced energy systems. Axions, if they exist, could interact with electromagnetic fields in ways that allow for highly efficient energy transfer or conversion. This could revolutionize technologies ranging from solar power to quantum computing. Axions are also prime candidates for explaining dark matter, suggesting that harnessing them might solve multiple cosmic mysteries simultaneously. Speaking of quantum computing, exotic matter could pave the way for next-generation computing technologies. Particles like Majorana fermions, which are theorized to be their own antiparticles, could enable qubits, quantum bits, that are far more stable and efficient than those used in current quantum computers. This stability would make quantum computing more practical, accelerating advancements in fields like artificial intelligence, cryptography, and complex system modeling. Exotic matter could also redefine our approach to space exploration and colonization. For example, negative mass or negative energy density could enable propulsion systems that defy conventional physics. In theory, a spacecraft using exotic matter could achieve faster-than-light travel by warping spacetime around it, a concept popularly known as the Alcubierre drive. While this idea remains speculative, it demonstrates how exotic matter could transform humanity from a planet-bound species to a truly interstellar civilization. The implications of exotic matter extend to fundamental physics experiments as well. High-energy particle accelerators, such as the Large Hadron Collider, are actively searching for signs of exotic particles predicted by theoretical models. These experiments could confirm the existence of particles like supersymmetric partners, which might constitute dark matter, or shed light on the properties of quark-gluon plasma. Each discovery adds a piece to the puzzle of understanding the universe's most enigmatic components. Exotic matter might also help resolve some of the most perplexing questions in cosmology, such as the nature of black hole interiors. The singularity at a black hole's core represents a breakdown of our current understanding of physics. Some theories suggest that exotic matter could exist in these extreme environments, preventing the singularity from forming or creating entirely new structures like white holes, which expel matter and energy instead of absorbing them. These ideas challenge our perception of black holes as cosmic dead ends, suggesting they might instead be gateways to new realms of physics. On a more speculative note, exotic matter raises the possibility of life beyond Earth. If exotic particles or states of matter can exist under extreme conditions, they might form the basis for entirely new forms of life. For example, life based on strange quark matter or other exotic substances could thrive in environments vastly different from those on Earth, such as the cores of neutron stars or the icy moons of gas giants. This expands the scope of astrobiology, encouraging scientists to consider a wider range of possibilities when searching for extraterrestrial life. The philosophical implications of exotic matter cannot be overstated. Its existence challenges our assumptions about reality, forcing us to confront questions about the nature of existence, the limits of human knowledge, and the interconnectedness of the cosmos. Each discovery in this field has the potential to reshape not only our scientific understanding but also our worldview, inspiring awe and curiosity in equal measure. As we delve deeper into the mysteries of exotic matter, one thing becomes clear: this is not just a journey of science but of imagination and wonder. The possibilities it unlocks are as boundless as the universe itself, promising a future where the impossible becomes reality. The exploration of exotic matter and its profound mysteries leads us into the realm of cosmological enigmas. One of the most fascinating aspects of exotic matter is its potential role in explaining dark energy, the mysterious force driving the accelerated expansion of the universe. While dark energy remains poorly understood, some theories suggest that exotic forms of matter with unusual properties, such as negative pressure, could provide the key to unraveling this cosmic puzzle. Negative pressure is a concept that defies ordinary intuition. In the context of exotic matter, it implies that such substances could exert a repulsive gravitational effect, pushing space apart rather than pulling it together. This aligns with observations of the universe's expansion, where galaxies are moving away from each other at an increasing rate. Exotic particles like axions or hypothetical scalar fields, such as quintessence, are often proposed as candidates for dark energy. If confirmed, these forms of exotic matter would not only explain the universe's behavior on the largest scales but also reveal new dimensions of physics beyond the standard model. Another intriguing possibility is that exotic matter could help solve the cosmic censorship hypothesis, a principle in general relativity that suggests singularities, points where space-time curvature becomes infinite, are always hidden within event horizons, making them unobservable. However, if exotic matter exists with properties that allow it to stabilize or alter singularities, it might challenge this hypothesis. For instance, negative energy could theoretically prevent the formation of event horizons, exposing singularities to direct observation. This would open a Pandora's box of questions about the nature of causality and the boundaries of spacetime. Exotic matter also plays a crucial role in multiverse theories, which propose the existence of multiple universes beyond our observable cosmos. Some models suggest that the creation of these universes involves exotic forms of energy or matter. For example, in eternal inflation theory, regions of space-time undergoing rapid expansion could give rise to pocket universes, each with its own physical laws. Exotic matter, particularly inflatons, might drive this process, acting as the seed for an endless array of alternate realities. If true, this concept would revolutionize our understanding of existence, suggesting that our universe is just one of countless others, each shaped by unique combinations of exotic forces and particles. On a smaller scale, exotic matter could offer insights into the quantum foam, the idea that spacetime itself is not smooth but instead consists of tiny, fluctuating structures at the Planck scale. Some theories predict that exotic particles or states of matter could interact with this quantum foam, revealing hidden dimensions or fundamental properties of spacetime. For instance, axions or other hypothetical particles might provide indirect evidence of quantum gravity, bridging the gap between the quantum and cosmic realms. The search for exotic matter also extends to high-energy astrophysical phenomena, such as gamma-ray bursts, neutron-star collisions, and black hole mergers. These events produce extreme conditions that could create or reveal exotic states of matter. For example, the collision of two neutron stars might produce strange quark matter or even more exotic phases, offering a unique glimpse into the behavior of matter at densities and temperatures far beyond anything achievable on Earth. Observations of these phenomena, combined with theoretical models, could help identify the signatures of exotic matter, bringing us closer to confirming its existence. In addition to astrophysics, exotic matter has profound implications for fundamental chemistry and materials science. If scientists can synthesize or isolate exotic substances, they could unlock unprecedented properties for technological applications. For example, materials with negative mass might exhibit frictionless motion, enabling new types of transportation systems or energy-efficient technologies. Similarly, the unique interactions of antimatter with ordinary matter could lead to breakthroughs in medicine, such as advanced imaging techniques. The potential applications of exotic matter in weaponry and defense also raise ethical concerns. Antimatter, for instance, could theoretically be used to create devastatingly powerful weapons, as its annihilation with matter releases enormous energy. While such applications are purely speculative at this stage, they underscore the dual-use nature of advanced scientific discoveries, highlighting the need for responsible stewardship of new technologies. In the realm of communication and information transfer, exotic matter could revolutionize how we share data across vast distances. Quantum entanglement, a phenomenon where particles become interconnected regardless of the space separating them, might be enhanced or facilitated by exotic states of matter. This could lead to faster-than-light communication systems or more secure quantum encryption methods, fundamentally changing how we interact in a connected universe. Exotic matter also offers tantalizing possibilities for terraforming and planetary engineering. By manipulating the properties of such matter, it might be possible to alter the environments of inhospitable worlds, making them suitable for human habitation. For example, exotic materials could be used to create stable artificial atmospheres, regulate temperatures, or even generate magnetic fields to shield colonies from cosmic radiation. These technologies could pave the way for humanity to become a multiplanetary species, fulfilling dreams of interstellar expansion. As we push the boundaries of our understanding, the quest to uncover exotic matter also confronts us with profound philosophical and existential questions. What does the existence of such matter imply about the nature of reality? Are the laws of physics as we understand them universal, or do they merely represent an approximation within our limited observational framework? The answers to these questions could redefine not only our scientific paradigms but also our place in the cosmos. Despite its promise, the study of exotic matter is fraught with challenges. Detecting and confirming its existence requires technologies and experimental setups that often verge on the limits of human capability. Particle accelerators, space telescopes, and deep underground detectors are just some of the tools scientists use to probe this elusive frontier. Each discovery, no matter how incremental, adds to our collective knowledge, inching us closer to unlocking the universe's deepest secrets. Exotic matter represents one of the most captivating frontiers in modern science. Its potential to reshape our understanding of the universe, from the smallest particles to the largest cosmic structures, is unparalleled. As we continue to explore its mysteries, we are reminded of the boundless curiosity that drives human progress, inspiring us to reach for the stars and beyond. The vast possibilities that exotic matter brings to theoretical physics and practical applications paint an exhilarating picture of the future. Yet, as we push deeper into the study of these materials, we face not only scientific but also philosophical dilemmas. The nature of exotic matter challenges the very foundation of our understanding of reality, prompting questions about the limits of human knowledge and the universe's underlying structure. One of the most mind-bending ideas involves exotic matter's potential role in simulated reality hypotheses. Some physicists and philosophers suggest that our universe could be a simulation, and exotic matter might serve as a telltale clue. For example, certain properties of exotic matter, like its ability to interact with hypothetical higher dimensions or manipulate spacetime, could suggest that our universe is governed by underlying computational rules. If exotic matter were discovered to behave in ways that resemble programmed systems, it would lend credence to the idea that we are part of a simulated environment, forcing humanity to reconsider its relationship with existence itself. This possibility connects deeply to the concept of fine-tuning in the universe. Scientists have long debated why the constants of nature, the strength of gravity, the charge of an electron, and other fundamental parameters, are so precisely calibrated to allow life to exist. Some propose that exotic matter could provide a missing piece in this puzzle. Perhaps the existence of certain exotic particles or fields influences the universe's constants, stabilizing them within a range that supports complexity. Such a discovery would offer not only an explanation for fine-tuning, but also a glimpse into the mechanisms shaping the cosmos. In the field of cosmic topology, exotic matter could help determine the universe's shape and size. While we often think of the universe as infinite, some models suggest it might have a finite yet unbounded shape, such as a higher-dimensional torus or a hypersphere. Exotic matter could be key to testing these theories, as its unique interactions with spacetime might reveal subtle distortions or patterns indicative of the universe's true geometry. This would allow us to map the cosmos in unprecedented detail, answering one of the oldest questions in cosmology: what does the universe look like on the largest scales? Exotic matter could also redefine our understanding of entropy and the arrow of time. In thermodynamics, entropy measures the disorder of a system, and its increase is associated with the forward flow of time. However, certain exotic states of matter might exhibit behaviors that challenge this principle, potentially reversing entropy in localized regions. If true, this could open up avenues for technologies capable of manipulating time at a quantum level, enabling everything from improved computing systems to speculative applications like time travel. While these ideas remain highly theoretical, they highlight the profound implications of exotic matter for fundamental physics. Turning our attention to astrophysics, exotic matter might provide answers to some of the most pressing questions about black holes. For instance, the information paradox, the apparent contradiction between quantum mechanics and general relativity regarding what happens to information that falls into a black hole, could find resolution in the properties of exotic matter. If strange or unknown particles exist near black holes, they might form structures, such as quantum hair, capable of storing information and preventing its loss. This would reconcile two pillars of modern physics and potentially reveal new ways to probe the event horizons of black holes. Exotic matter also intersects with the study of cosmic strings, theoretical one-dimensional defects in spacetime that might have formed during the universe's earliest moments. These strings, if they exist, could host exotic particles along their lengths, creating regions of intense gravitational and electromagnetic activity. By studying these phenomena, scientists could learn more about the conditions of the early universe, including the forces that shaped its evolution and the formation of fundamental particles. In the context of galactic formation, exotic matter might play a role in shaping the structure of the universe. For instance, dark matter, a form of exotic matter that interacts gravitationally but not electromagnetically, is thought to have been crucial in the formation of galaxies. Without its gravitational pull, the early universe might not have had enough mass to overcome the expansion driven by dark energy, preventing the formation of stars, planets, and eventually life. By studying dark matter and its interactions with other exotic substances, we can gain a deeper understanding of how the cosmos came to be. Exotic matter also holds promise for uncovering the secrets of cosmic acceleration, the mysterious increase in the universe's rate of expansion. While dark energy is often cited as the cause, some theories suggest that certain exotic particles or fields could produce this effect. If so, understanding these entities might allow us to predict the universe's ultimate fate. Will it continue expanding forever, leading to a heat death? Or will it eventually reverse course in a big crunch? Exotic matter could provide the answers. On a more speculative note, exotic matter might offer solutions to the problem of interstellar communication. Current methods, such as radio waves, are limited by the speed of light and the vast distances between stars. However, exotic particles capable of tunneling through space-time or interacting with higher dimensions might enable near-instantaneous communication across cosmic distances. Such a breakthrough would not only revolutionize how civilizations within our galaxy interact but also open the door to contact with intelligent extraterrestrial life. In terms of extraterrestrial exploration, exotic matter could pave the way for entirely new propulsion systems. For example, antimatter engines, which convert matter and antimatter into pure energy, could provide the thrust needed to reach distant stars within human lifetimes. Similarly, negative energy fields might enable the creation of stable wormholes, allowing spacecraft to traverse enormous distances instantaneously. These advancements would transform space travel from a distant dream into a practical reality, enabling humanity to explore the galaxy and beyond. The potential applications of exotic matter also extend to terraforming alien worlds. By harnessing its unique properties, such as energy production or gravitational manipulation, it might be possible to modify the environments of planets like Mars or Europa, making them suitable for human habitation. This would mark a significant step in humanity's evolution, allowing us to become a multiplanetary species and ensuring our survival in the face of existential threats on Earth. The study of exotic matter serves as a reminder of the vast unknowns that still lie ahead. Each discovery raises new questions, pushing the boundaries of what we understand about the universe and our place within it. As we continue to explore this frontier, we are not only expanding the limits of human knowledge, but also redefining what it means to be curious, inventive, and alive. Exotic matter's implications are so profound that they challenge our existing frameworks of understanding, compelling us to reconsider fundamental principles that have guided science for centuries. At its core, exotic matter forces us to grapple with concepts that blur the boundaries between physics, metaphysics, and even philosophy. For example, it raises questions about the nature of causality, the relationship between cause and effect. If certain exotic particles or fields allow for backward causation or the reversal of time in localized areas, then our understanding of linear time may be incomplete. This idea is deeply unsettling yet exciting, as it hints at entirely new dimensions of reality yet to be explored. In the realm of quantum mechanics, exotic matter introduces puzzles that could potentially rewrite our understanding of the quantum world. Consider the phenomenon of quantum entanglement, where two particles remain connected regardless of the distance between them. Some theories suggest that exotic matter could amplify or stabilize this entanglement, leading to more robust quantum networks. This could revolutionize computing, enabling the development of quantum systems with unparalleled processing power and precision. It could also have implications for secure communication, as quantum entanglement is immune to traditional eavesdropping methods. Another intriguing aspect of exotic matter lies in its potential role in quantum field theory. Fields like the Higgs field are known to impart mass to particles, but the existence of exotic fields could introduce new forces or modify the interactions between existing particles. This might explain anomalies observed in particle physics experiments, such as unexplained energy levels or deviations in particle decay rates. Understanding these fields could open up new avenues for unifying quantum mechanics with general relativity, a goal that has eluded physicists for decades. On a cosmic scale, exotic matter could illuminate mysteries surrounding the multiverse theory, which posits that our universe is just one of countless others. Some models suggest that exotic particles, like Axions or strange matter, might serve as bridges or indicators of interactions between universes. For instance, if Axions are found to exist, their properties could provide clues about how energy flows between parallel universes or how they influence each other. This would not only validate the multiverse hypothesis but also offer a framework for exploring it scientifically. The potential for exotic matter to serve as a medium for energy transfer is also worth considering. In particular, it could enable breakthroughs in energy harvesting and storage. Imagine materials capable of storing vast amounts of energy in exotic states, releasing it on demand with unparalleled efficiency. This could revolutionize industries ranging from renewable energy to space exploration, where efficient energy use is paramount. Exotic matter might even lead to the development of infinite energy systems, though the ethical and environmental consequences of such technologies would require careful consideration. In addition to practical applications, exotic matter might also redefine how we understand entropy and information in the universe. Some physicists propose that exotic particles could act as carriers of cosmic information, encoding the history and structure of the universe itself. If we could decipher this information, it might provide insights into the origins of the cosmos, the nature of time, and even the eventual fate of existence. This idea resonates with the concept of the universe as a vast computational system, where exotic matter plays the role of a storage medium or processing unit. The potential for exotic matter to impact human evolution cannot be overlooked. For instance, its properties could be harnessed to enhance biological systems, creating new possibilities for longevity, resilience, and even intelligence. Materials derived from exotic matter might be used to develop implants or devices that interface directly with the human nervous system, enhancing our cognitive and physical capabilities. This could mark the beginning of a new era in which humanity transcends its biological limitations, merging with technology to explore the cosmos in ways currently unimaginable. Furthermore, exotic matter might hold the key to understanding the origins of consciousness. Some theories suggest that consciousness arises from quantum processes in the brain, and exotic particles or fields could play a role in these processes. If true, studying exotic matter might provide insights into the nature of awareness, free will, and the mind's connection to the physical world. This would not only have profound implications for neuroscience and psychology, but also challenge long-standing philosophical debates about the nature of self and reality. As we consider the ethical implications of exotic matter, it becomes clear that its discovery and utilization would require careful regulation and oversight. The potential for misuse, particularly in the development of weapons or other destructive technologies, is significant. For example, antimatter bombs, if feasible, could produce explosions far more powerful than any nuclear weapon. Similarly, the ability to manipulate space-time or create artificial black holes could have catastrophic consequences if used irresponsibly. International cooperation and stringent safeguards would be essential to ensure that exotic matter is used for the betterment of humanity rather than its detriment. The study of exotic matter also has cultural and societal implications. It challenges deeply ingrained beliefs about the universe and our place within it, forcing humanity to confront the possibility that much of what we consider impossible may simply lie beyond our current understanding. This could lead to a new era of intellectual and spiritual exploration, as people grapple with the implications of discoveries that redefine the boundaries of possibility. Despite the challenges and uncertainties, the pursuit of knowledge about exotic matter is a testament to humanity's enduring curiosity and resilience. It represents the frontier of scientific inquiry, where each discovery opens up new questions and possibilities. As we continue to explore this uncharted territory, we are reminded of the vast potential of human ingenuity and the infinite mysteries of the cosmos. Exotic matter, in all its forms, embodies the promise of a future where science and imagination converge, unlocking the secrets of the universe and paving the way for innovations that will shape generations to come. It is a journey that is as much about discovery as it is about wonder, inviting us to look beyond the stars and into the very fabric of reality itself. As we dive deeper into the mysteries surrounding exotic matter, it's essential to highlight that the concept of strange matter is one of the most fascinating yet perplexing aspects of this field. Strange matter is thought to consist of quarks, fundamental particles that combine to form protons and neutrons in ordinary matter, but in a more exotic form. Unlike the up and down quarks that make up normal matter, strange matter includes strange quarks, which are heavier and more unstable than their counterparts. The theoretical existence of strange matter arises from the possibility that under extreme conditions, such as inside neutron stars or during the collapse of massive stars, matter could form a more stable structure made of quarks in a different configuration. Imagine a piece of this strange matter, which would be far denser than anything we encounter in our everyday lives. If strange matter were to interact with ordinary matter, the results could be catastrophic. It might convert regular matter into more strange matter, causing an unstoppable process of matter transformation, potentially obliterating planets, stars, and even galaxies. However, this is purely speculative at this stage, with no direct evidence to confirm the existence of strange matter. Yet, its potential to radically change our understanding of matter and the forces that govern the universe is undeniable. Strange matter is also closely tied to the phenomenon of neutron stars, which are among the densest objects in the universe. These stars, formed when a massive star exhausts its nuclear fuel and collapses under gravity, are believed to contain an environment ripe for the creation of exotic forms of matter. The extreme pressures inside neutron stars might be sufficient to produce strange matter, or at least quark matter, in which quarks are no longer confined to individual protons or neutrons but are free to roam within a dense, fluid-like structure. Understanding how these strange forms of matter behave could unlock answers about the fundamental forces that govern not only stars but the very nature of matter itself. Beyond strange matter, we must also consider antimatter, which holds an especially significant place in the history of physics. Antimatter is composed of particles that have the opposite electrical charge to their corresponding matter counterparts. For example, while a proton has a positive charge, an antiproton has a negative charge. When matter and antimatter meet, they annihilate each other in a burst of energy, as their opposite charges cancel out. This annihilation is a highly efficient process of energy conversion, releasing vast amounts of energy in the form of gamma rays. One of the most perplexing mysteries of the universe is the matter-antimatter asymmetry. According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. However, we observe a universe almost entirely composed of matter, with very little antimatter detectable in the observable cosmos. This discrepancy has puzzled scientists for decades. If there is so much antimatter out there, why don't we see it around us? The search for an explanation continues to drive research in cosmology and particle physics, as finding even a small amount of antimatter could hold the key to understanding the birth and evolution of the universe itself. One of the more exciting prospects involving antimatter is its potential as a source of energy. In theory, small amounts of antimatter could be used as an incredibly powerful fuel. For instance, a gram of antimatter could release more energy than a kiloton of TNT when annihilated with an equal amount of matter. This suggests that if we could find ways to produce, store, and control antimatter, it could revolutionize energy generation, propulsion systems, and even space travel. The development of antimatter-powered spacecraft, for example, could make interplanetary or even interstellar travel feasible, something that currently lies beyond our reach. But the technical hurdles are immense. Antimatter is incredibly difficult to produce, and it is even harder to contain and store without it annihilating against the walls of its container. At this point, antimatter research is still in its infancy. Scientists have been able to create tiny amounts of antimatter in particle accelerators, but these quantities are minuscule, on the order of billionths of a gram. Moreover, the production process requires enormous amounts of energy, and the containment of antimatter is a significant challenge due to the fact that it must be isolated from matter to avoid annihilation. The development of magnetic traps, which use strong magnetic fields to keep antimatter suspended in a vacuum, is one of the most promising methods being explored. However, this technology is far from being practical for large-scale energy production. Interestingly, antimatter isn't just a theoretical idea with distant applications. Some scientists have proposed that antimatter could play a role in the behavior of black holes and other extreme astrophysical phenomena. For instance, certain models suggest that black holes might not only contain massive amounts of regular matter but could also have regions where antimatter is concentrated. This could lead to new insights into the nature of black holes, their formation, and their relationship with the surrounding universe. Further beyond antimatter, there are other exotic particles theorized by physicists that could change the way we think about the universe. One such particle is the Axion, a hypothetical particle that has been proposed to explain a number of unresolved phenomena in physics, including the behavior of certain subatomic particles. Axions are extremely light and weakly interacting, making them difficult to detect with current instruments. However, their potential implications for cosmology and particle physics are vast. For one, Axions might help explain the mysterious dark matter that seems to constitute a significant portion of the universe's mass but cannot be observed directly. If Axions exist, they could be a major component of dark matter, and finding them would represent one of the most significant discoveries in modern physics. Another reason Axions are so intriguing is their potential role in quantum computing. Because Axions are incredibly stable, they could potentially be used in creating new types of quantum bits, or qubits, for quantum computers. This would allow quantum computers to function in ways that are vastly more efficient than current technology allows, opening up new possibilities for computing, encryption, and information processing. The search for Axions and other exotic particles is ongoing, and it requires some of the most advanced scientific equipment available. Experiments like the Axion Dark Matter Experiment, ADMEX, are specifically designed to detect axions by looking for the faint signals they might produce when exposed to magnetic fields. If these particles exist, they could provide a critical link in our understanding of the fundamental forces of nature. As we continue to explore the farthest reaches of theoretical physics and experiment with new technologies, exotic matter remains one of the most promising yet mysterious frontiers. From its role in the formation of the universe to its potential in unlocking the secrets of dark matter and dark energy, exotic matter holds the key to some of the most profound questions in science. Whether it's through the discovery of strange matter, antimatter, axions, or other unknown particles, we are on the cusp of uncovering the true nature of the cosmos, and in doing so, we may find the answers to questions humanity has asked for centuries. The pursuit of understanding exotic matter is not just about answering fundamental questions, it's also about the possibilities it offers for advancing technology, improving life on Earth, and perhaps even opening the door to the exploration of other worlds. As we push the boundaries of our knowledge and develop the tools to explore these strange and unknown forms of matter, we stand on the precipice of a new era of discovery, one that could radically reshape our understanding of the universe and our place within it. The search for exotic matter could have profound implications not only for our understanding of the cosmos but also for practical technological advancements that are currently beyond our imagination. One of the most significant fields where the discovery of exotic matter could have a transformative impact is in space exploration. As we venture further into the universe, our current methods of propulsion and energy generation are limited by the available technology. Traditional rockets, despite their impressive engineering, are constrained by fuel capacity, efficiency, and the immense distances involved in interstellar travel. This is where exotic matter could step in to change the game. One of the most exciting possibilities is that exotic forms of matter, such as antimatter or strange matter, could be harnessed as highly efficient energy sources for spacecraft propulsion. Imagine spacecraft powered by antimatter engines, where the energy released by the annihilation of matter and antimatter could provide a nearly infinite supply of energy. With such technology, spacecraft could travel vast distances in a fraction of the time it would take with current propulsion systems. Theoretically, antimatter-powered engines could reduce travel time to distant planets, even to other star systems, to mere decades instead of thousands of years. Another idea being explored is the potential use of warp drives, a concept based on the manipulation of spacetime itself. In 1994, physicist Miguel Alcubierre proposed a theoretical model in which a spacecraft could achieve faster-than-light travel by contracting space in front of it and expanding space behind it, effectively creating a warp bubble that moves faster than the speed of light without violating the laws of physics. Although this idea remains purely theoretical and faces many challenges, exotic matter, particularly in the form of negative energy, could be essential for creating the conditions required for a warp drive. Negative energy is a concept linked to exotic matter that has properties opposite to those of normal matter, enabling the creation of a warp bubble, or even a stable wormhole. The existence of exotic forms of matter, like negative energy, could be the key to unlocking the possibility of interstellar travel. Beyond propulsion systems, exotic matter also offers tantalizing possibilities for energy generation here on Earth. As mentioned earlier, antimatter holds incredible potential as a power source. If we could find a way to produce, store, and safely manage antimatter, it could revolutionize the energy sector. The amount of energy generated by even small quantities of antimatter annihilation is staggering. For instance, just 1 gram of antimatter could theoretically release the same amount of energy as a nuclear bomb, but without the harmful radiation and byproducts that come with conventional nuclear reactions. The application of antimatter as a clean, efficient energy source could solve many of the world's energy problems and even reduce our reliance on fossil fuels, significantly mitigating the effects of climate change. Moreover, exotic matter may also play a role in future medical technologies. Imagine the potential of using antimatter in positron emission tomography, PET scans, a medical imaging technique that already relies on positrons, the antimatter counterpart of electrons. While current PET scans are extremely valuable for detecting diseases, the use of larger quantities of antimatter could improve the resolution and effectiveness of these scans, allowing for even more precise diagnoses. On a larger scale, the study of exotic matter may also lead to breakthroughs in quantum computing. Quantum computers leverage the unique properties of quantum mechanics to process information in ways that traditional computers cannot. These quantum bits, or qubits, can exist in multiple states simultaneously, allowing quantum computers to solve complex problems much more quickly than classical computers. However, to make quantum computers practical on a large scale, we need more stable and efficient methods for creating and manipulating qubits. Exotic particles like axions could play a critical role in developing new forms of quantum bits, creating more powerful and efficient quantum computers. These advancements could revolutionize fields ranging from cryptography and artificial intelligence to drug discovery and climate modeling. While the potential applications of exotic matter are exciting, it is crucial to understand that we are still in the early stages of uncovering its mysteries. Much of the research on strange matter, antimatter, and axions is theoretical, and direct experimental evidence remains elusive. The detection and manipulation of exotic matter require technologies that are far beyond our current capabilities. But that should not diminish the excitement that comes from exploring these ideas. The search for exotic matter is one of the most thrilling aspects of modern physics and cosmology, and the discoveries we make could redefine our understanding of the universe in ways we can't yet imagine. One of the reasons we've yet to discover exotic matter in any meaningful way is the immense energy scales involved in creating these substances. For instance, to produce even tiny amounts of antimatter, we need particle accelerators that can reach the energy levels required to generate such high-energy particles. These accelerators, like the Large Hadron Collider, LHC, at CERN, are capable of smashing protons together at near-light speeds, but even they are not designed to produce large quantities of antimatter. The production of antimatter is extremely inefficient, and the energy required to create it currently far exceeds the energy we get from its annihilation. Until we can find a way to produce antimatter more efficiently and in larger quantities, it will remain largely a theoretical curiosity. Moreover, containing antimatter presents another enormous challenge. Since antimatter annihilates when it comes into contact with normal matter, scientists must find ways to store it in a vacuum, isolated from matter, using magnetic fields or other advanced methods. Currently, antimatter can only be stored for fractions of a second before it annihilates. The technological and engineering hurdles to overcome in order to build practical devices that can harness antimatter's power are substantial, and the risk of accidental annihilation in an uncontrolled environment would be catastrophic. Similarly, strange matter remains a theoretical construct, with no experimental evidence suggesting that it exists in any substantial form outside the extreme environments of neutron stars or potentially in the aftermath of black hole collisions. As with antimatter, scientists are using advanced technologies to detect and study exotic forms of matter, but much remains unknown about the conditions under which strange matter might be produced or whether it could be manipulated for practical use. The study of exotic matter is one of the most exciting frontiers in modern science, but it is also one of the most challenging. It requires breakthroughs in both theory and technology that will take time to achieve. However, the potential rewards of discovering and harnessing exotic matter are so immense that it is a pursuit worth following. Whether it leads to new energy sources, faster-than-light travel, or quantum computers that revolutionize industries, the exploration of exotic matter could change the course of human history. The universe is full of mysteries, and exotic matter is one of its most tantalizing puzzles, waiting to be unlocked. The quest for exotic matter is not just confined to academic researchers and theoretical physicists. It has the potential to inspire entire generations of engineers, innovators, and dreamers who will contribute to the advancement of technologies that could reshape the future. The study of exotic matter is pushing the boundaries of human knowledge and technology, often in ways we can't yet fully comprehend. As we continue to explore these strange forms of matter, we may discover more about the fundamental forces of the universe, uncovering deep connections between matter, energy, and space-time itself. One of the most exciting aspects of exotic matter is how it challenges our understanding of the universe. For centuries, we believed that matter and energy were the only building blocks of reality. However, the discovery of exotic matter forces us to reconsider this worldview. Negative energy, strange quarks, Axions, and antimatter all exist in realms that defy our conventional understanding of physics. These new forms of matter don't behave in the predictable ways we are used to, and this adds a layer of intrigue to the fundamental nature of the universe. Could these exotic forms of matter help us better understand the dark energy that drives the accelerated expansion of the universe, or dark matter, which is responsible for the structure of galaxies? Could they provide us with insights into the Big Bang and the earliest moments of the universe's existence? The quest for exotic matter is, in many ways, tied to our understanding of the unified field theory, a framework that seeks to explain all the fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, within a single, comprehensive theory. Some scientists believe that exotic matter could provide a window into this elusive theory, revealing how these forces interact at the most fundamental level. If we could find a way to manipulate exotic matter, we might unlock the secrets of the cosmos, including the unification of all forces, and gain a deeper understanding of gravity, quantum mechanics, and relativity. In addition to these theoretical considerations, the discovery and manipulation of exotic matter could have profound implications for our technological landscape. For instance, it could lead to advancements in energy generation, power storage, and propulsion systems that would be impossible with current materials. Imagine cities powered entirely by antimatter reactors, emitting little to no waste, creating energy without harmful emissions, and providing a clean, sustainable alternative to fossil fuels. Think about space colonies powered by exotic forms of matter, where vast populations can thrive in far-flung corners of the galaxy, connected by efficient, warp-speed travel. The advent of exotic matter might be the key to realizing the dreams of space exploration that were once thought to be the realm of science fiction. But with great power comes great responsibility. Harnessing exotic matter is not without risks. As exciting as the possibilities are, we must approach these breakthroughs with caution. The potential for misuse, whether in the form of catastrophic energy releases or dangerous weaponry, is a serious concern. Antimatter, in particular, is incredibly volatile. Even small amounts of antimatter can release massive amounts of energy when they come into contact with normal matter. If antimatter were to fall into the wrong hands, the consequences could be disastrous. Likewise, the discovery of strange matter could have unforeseen consequences if not carefully controlled. Strange matter is theorized to be highly stable, even at extreme temperatures and pressures, and there is a possibility that it could convert normal matter into strange matter upon contact, leading to a catastrophic, strange matter, event. While such scenarios are purely speculative, the risks involved in working with exotic matter must be taken seriously. This brings us to another crucial consideration: the ethics of researching and potentially harnessing exotic matter. As we unlock the secrets of the universe, we must consider the ethical implications of using such knowledge. Could the discovery of exotic matter lead to dangerous technologies being developed faster than we can understand their consequences? Would it be possible for certain groups or governments to use exotic matter for military purposes, creating weapons of mass destruction far beyond the scope of anything we have today? These questions raise serious concerns about how we approach the future of science and technology. As we continue to explore the frontiers of physics and cosmology, we must also ask ourselves how we can ensure that the knowledge we gain is used responsibly and ethically. The pursuit of exotic matter is a journey of exploration, innovation, and imagination. It forces us to stretch the limits of what we know and encourages us to think outside the box. Although we are still in the early stages of understanding these bizarre forms of matter, the potential rewards are immense. From revolutionizing our energy systems to unlocking the secrets of the universe, the discovery of exotic matter could lead to breakthroughs that change the course of history. As we move forward, we must continue to explore the strange and unknown regions of the universe, expanding our knowledge and challenging our understanding of reality. The mysteries of exotic matter remind us that the universe is far more complex and strange than we could ever have imagined. It is a reminder that there is still so much we don't know, and that there may be entire realms of existence just waiting to be discovered. The quest for exotic matter is not just about uncovering new forms of matter, but also about exploring the fundamental principles that govern the universe. It is a journey that transcends the boundaries of science and touches on the very essence of who we are as humans. In the search for strange matter, antimatter, and axions, we are not only unlocking the secrets of the cosmos but also unlocking our own potential. The future is full of possibilities, and exotic matter may just be the key to unlocking them. As we continue to delve into these unknown realms, we may discover that the universe is far stranger, more complex, and more beautiful than we ever imagined. Exotic matter is one of the many mysteries that we will continue to explore, and it is a journey that promises to take us to places we can only dream of. Exotic matter represents one of the most profound enigmas in our understanding of the cosmos, and the possibilities it offers are as vast as the universe itself. The continued exploration of strange matter, antimatter, axions, and other theoretical entities not only fuels our scientific curiosity but also has the potential to revolutionize the way we perceive and interact with reality. Each step forward in our understanding brings with it new questions, challenges, and opportunities that could reshape human existence on a scale previously thought unimaginable. One of the areas where exotic matter could have the most profound impact is in the field of cosmology. Theoretical physics often presents us with paradoxes and unanswered questions that exotic matter might help resolve. For instance, consider the concept of dark matter, which makes up roughly 27% of the universe's mass energy content. Despite its prevalence, dark matter has never been directly observed, and its true nature remains one of the greatest mysteries in physics. Some scientists theorize that exotic particles, such as axions or sterile neutrinos, could form the backbone of dark matter, providing the gravitational scaffolding that holds galaxies together. If this hypothesis is correct, then understanding exotic matter might not just be a fringe pursuit. It could be the key to deciphering the very fabric of the cosmos. The implications for astronomy are equally groundbreaking. Exotic matter might provide insights into some of the most extreme and fascinating objects in the universe, such as neutron stars, black holes, and quasars. Strange matter, for instance, is often associated with the theoretical concept of strange stars, a type of compact star thought to exist at even higher densities than neutron stars. If these objects do exist, they would challenge our understanding of how matter behaves under intense gravitational and nuclear forces. Observing and studying such phenomena could offer unprecedented insights into the limits of physics and the behavior of matter in extreme conditions. Furthermore, exotic matter is intrinsically linked to the quest for understanding dark energy, the mysterious force driving the accelerated expansion of the universe. While dark energy remains poorly understood, some researchers believe that certain types of exotic particles or fields could play a role in its behavior. Unraveling this mystery could transform our comprehension of the universe's ultimate fate, whether it will expand forever, collapse back on itself, or reach some other unexpected conclusion. Beyond the cosmos, exotic matter could redefine the boundaries of human achievement through its applications in advanced technologies. Consider the potential of antimatter propulsion systems for space travel. In theory, antimatter could serve as the most efficient fuel source imaginable, as its annihilation with normal matter releases vast amounts of energy. While the challenges of producing and storing antimatter are currently insurmountable, Breakthroughs in this area could enable spacecraft capable of traveling at relativistic speeds, bringing distant stars and exoplanets within our reach. Such a development would not only mark a new era in space exploration but also raise profound questions about humanity's place in the universe. Even on Earth, exotic matter could revolutionize everyday life. Imagine materials with properties derived from exotic states of matter, such as superconductors that operate at room temperature or ultra-strong, ultralight materials formed from strange quark interactions. These advancements could transform industries ranging from energy and transportation to computing and healthcare, unlocking levels of efficiency and innovation previously thought unattainable. However, as tantalizing as these possibilities are, the pursuit of exotic matter is fraught with challenges. For one, many forms of exotic matter are inherently unstable, existing only under very specific conditions or for fractions of a second in high-energy environments like particle accelerators. This makes studying them exceptionally difficult and requires technologies that are still in their infancy. Moreover, the ethical and safety concerns surrounding exotic matter cannot be ignored. The immense energy densities associated with antimatter, for example, make it both a potential energy source and a devastating weapon. As such, any progress in this field must be accompanied by rigorous oversight and international collaboration to ensure that it is used responsibly. The pursuit of exotic matter also raises profound philosophical questions about the nature of reality and humanity's role in it. If exotic matter holds the key to understanding the universe's most fundamental mysteries, what does that say about the limitations of our current knowledge? Are we merely scratching the surface of a much deeper, more complex reality? And if we do succeed in harnessing the power of exotic matter, how will that reshape our relationship with the cosmos and with each other? These questions are not just academic, they strike at the heart of what it means to be human. The exploration of exotic matter is, in many ways, a continuation of the age-old quest to understand our origins, our purpose, and our destiny. It is a journey that requires not only scientific ingenuity but also imagination, courage, and a deep sense of responsibility. As we stand on the cusp of new discoveries, we are reminded that the universe is far stranger and more wondrous than we can comprehend, and that our pursuit of knowledge is both a privilege and a profound obligation. The story of exotic matter is far from over. With each experiment, each observation, and each breakthrough, we move closer to unlocking its secrets and harnessing its potential. In doing so, we are not only expanding the boundaries of human knowledge, but also charting a path toward a future where the impossible becomes possible. The journey ahead will be challenging, but it is one that we must undertake, for in the mysteries of exotic matter lie the keys to understanding the universe and our place within it. The journey into the realm of exotic matter is like peeling back the layers of an infinite onion, each discovery revealing new depths of complexity and wonder. As scientists continue to probe the secrets of strange matter, antimatter, axions, and other exotic particles, they are not only uncovering the intricate tapestry of the universe but also challenging our most fundamental assumptions about reality itself. One area where exotic matter holds immense promise is in quantum physics. Quantum mechanics has always defied classical logic, introducing phenomena like superposition and entanglement that seem to operate outside the rules of everyday experience. Exotic matter, with its peculiar properties and behaviors, often appears to be at home in this quantum realm. For example, the study of axions has led to speculation about their role in creating coherent quantum states that might influence the large-scale structure of the universe. These quantum effects could provide new insights into the nature of gravity, time, and even the mysterious phenomenon of consciousness. The connection between exotic matter and quantum computing is another avenue ripe for exploration. Quantum computers, which rely on the principles of superposition and entanglement, are already pushing the boundaries of computational power. If exotic matter could be harnessed to create more stable qubits or reduce decoherence, it might pave the way for quantum machines capable of solving problems that are currently beyond human comprehension. From simulating complex biological processes to decrypting advanced encryption codes, such advancements could revolutionize fields as diverse as medicine, cybersecurity, and artificial intelligence. But the implications of exotic matter go far beyond practical applications. Consider the concept of multiverses, a hypothesis in which our universe is just one of an infinite number of parallel realities. Some theoretical physicists suggest that exotic matter might serve as a bridge or an indicator of interactions between these universes. For instance, the peculiar properties of antimatter and strange matter might reflect physical laws that differ from our own, hinting at the existence of alternate dimensions. If this is true, then the study of exotic matter could lead us to a greater understanding of the multiverse and our place within it. The idea of time travel is another tantalizing frontier. While still firmly in the realm of science fiction, certain theories propose that exotic matter could stabilize wormholes or create negative energy densities necessary for bending spacetime. If such concepts were ever realized, they would not only redefine our understanding of time but also raise profound ethical and philosophical questions. Could humanity be trusted with the power to alter the past or glimpse into the future? What responsibilities would come with such a capability? On the cosmic scale, exotic matter could also play a critical role in understanding cosmic inflation, the rapid expansion of the universe that occurred moments after the Big Bang. Some scientists theorize that fields associated with exotic particles, such as axions or scalar fields, could have driven this inflationary period, shaping the universe's large-scale structure. By studying these particles, researchers hope to uncover clues about the very beginnings of existence, potentially answering questions about why the universe exists at all. The implications for astrophysics are equally profound. Exotic matter might explain the behavior of pulsars, the rapidly spinning remnants of massive stars, or even shed light on the enigmatic nature of magnetars, which possess magnetic fields billions of times stronger than anything on Earth. These celestial phenomena are not just fascinating in their own right. They also serve as natural laboratories for testing the limits of physical laws and exploring the properties of exotic matter under extreme conditions. Closer to home, exotic matter could transform our understanding of the Earth's core and the fundamental processes that drive planetary systems. Some researchers speculate that tiny amounts of strange matter or other exotic particles might exist deep within the Earth, influencing geophysical phenomena like plate tectonics and magnetic field generation. If true, this could open up entirely new fields of study and provide insights into the planet's long-term stability and habitability. As we look to the future, the study of exotic matter also raises important questions about humanity's role in the universe. Are we merely passive observers of these phenomena, or do we have a more active part to play? The possibility of harnessing exotic matter for energy, transportation, or even the creation of entirely new materials suggests that humanity could one day become a cosmic architect, shaping the universe to suit our needs and ambitions. However, such power would come with immense responsibility, requiring careful consideration of the ethical and environmental consequences of our actions. The pursuit of exotic matter is not just a scientific endeavor, it is a testament to the human spirit. It embodies our innate curiosity, our desire to push boundaries, and our relentless quest for knowledge. Each discovery, no matter how small, brings us closer to understanding the intricate web of forces and particles that make up our reality. And with each breakthrough, we are reminded of the infinite possibilities that await us, both within the universe and within ourselves. The study of exotic matter is more than just a journey through the cosmos, it is a journey into the very heart of existence. It challenges us to question our assumptions, to expand our horizons, and to embrace the unknown with courage and imagination. Whether we are peering into the depths of a neutron star, unraveling the mysteries of dark matter, or dreaming of interstellar travel, we are united by a common goal: to uncover the secrets of the universe and to find our place within its infinite expanse. And so, as we continue to explore the strange and unknown forms of matter that lie at the edge of our understanding, we do so with the knowledge that each discovery brings us closer to the ultimate truth, that the universe is not just a collection of stars and particles, but a boundless frontier of possibilities, waiting to be discovered. The quest to understand exotic matter goes hand in hand with unraveling the deepest mysteries of the cosmos. It's not merely about cataloging strange particles or predicting their behaviors, but also about seeking answers to the fundamental questions of existence. What is the universe made of? What forces govern its behavior? And most intriguingly, what possibilities lie beyond the boundaries of our current knowledge? One of the most compelling aspects of exotic matter is how it challenges our understanding of conservation laws, the bedrock principles of physics that dictate how energy, mass, and momentum are preserved. Take antimatter, for example. When matter and antimatter meet, they annihilate each other, converting entirely into energy. This process is the most efficient energy conversion known, far surpassing chemical or nuclear reactions. If we could harness antimatter safely and economically, it could revolutionize energy generation, providing an almost limitless source of power. This potential extends to propulsion systems for space exploration. Antimatter engines, theoretically capable of reaching a significant fraction of the speed of light, could make interstellar travel feasible within a human lifetime. Such technology could enable missions to distant star systems, or even allow us to establish a human presence beyond our solar system. However, the production and storage of antimatter remain colossal challenges. Current methods are incredibly inefficient, producing only minute quantities at an astronomical cost. Yet, the promise of such technology continues to inspire engineers and scientists alike. Strange matter, on the other hand, offers a different kind of allure. Its incredible density could make it the ultimate building material for futuristic technologies. Imagine spacecraft reinforced with layers of strange matter, impervious to the intense pressures of black holes or the extremes of cosmic radiation. Such applications, while speculative, underscore the transformative potential of exotic matter. But what of the role these particles might play in the natural world? Some theorists propose that strange matter could exist in the cores of neutron stars, where conditions of immense pressure and density push atomic structures to their limits. These so-called quark stars or strange stars could provide a testing ground for our understanding of quantum chromodynamics, the theory that describes the interactions of quarks and gluons. Observing such stars could validate or refute decades of theoretical work, offering a rare glimpse into the universe's most extreme environments. Similarly, axions, if they exist, could help solve the puzzle of dark matter, a substance that comprises approximately 27% of the universe yet eludes direct detection. Unlike other dark matter candidates, axions are incredibly light and interact weakly with ordinary matter. They could form vast, diffuse halos around galaxies, influencing their rotation and structure. Detecting axions would not only confirm their existence but also provide a window into the invisible scaffolding that shapes the universe. The implications of exotic matter extend beyond the physical realm, touching on philosophical and even metaphysical questions. If axions or other exotic particles are found to permeate all of space, influencing matter and energy at a fundamental level, could they represent the elusive ether, once hypothesized by early physicists? Or might they be the threads of a deeper, more unified reality, tying together the seemingly disparate forces of nature? These questions lead us to the concept of theory unification, the long-sought goal of combining quantum mechanics and general relativity into a single, coherent framework. Exotic matter could play a pivotal role in achieving this unification. For example, string theory, one of the leading candidates for a unified theory, predicts the existence of particles with properties strikingly similar to those of exotic matter. If these particles are observed, it could lend credence to string theory and bring us closer to understanding the universe's most fundamental forces. However, this pursuit is not without its risks. Manipulating exotic matter, particularly antimatter, comes with potential dangers. A single gram of antimatter, if mishandled, could release energy equivalent to a nuclear bomb. Similarly, creating stable configurations of strange matter might lead to unforeseen consequences, such as triggering a chain reaction that converts ordinary matter into strange matter. These risks underscore the need for rigorous safety protocols and ethical guidelines as we continue to explore this frontier. The search for exotic matter also serves as a reminder of the interconnectedness of science and technology. Advances in particle accelerators, such as the Large Hadron Collider, have enabled the detection of rare particles and the recreation of extreme conditions similar to those in neutron stars or the early universe. Meanwhile, breakthroughs in materials science and quantum computing are providing new tools for studying and utilizing exotic matter. This synergy highlights the collaborative nature of scientific progress, where discoveries in one field often fuel innovations in another. Moreover, the exploration of exotic matter reflects humanity's enduring curiosity and ambition. It is a testament to our ability to dream beyond our limitations, to imagine possibilities that transcend the ordinary. Whether we are deciphering the secrets of Axions, harnessing the power of antimatter, or contemplating the nature of strange matter, we are, at our core, seekers of knowledge. This relentless pursuit is what propels us forward, guiding us through the unknown and illuminating the mysteries of the cosmos. Exotic matter, with all its strangeness and potential, is not just a subject of scientific inquiry, it is a symbol of our shared journey into the depths of existence. As we continue to explore its properties and implications, we are not only expanding our understanding of the universe but also redefining what it means to be human. The journey to uncover the mysteries of exotic matter leads us deeper into the fabric of reality, raising questions about the limits of our understanding and the boundless potential for discovery. Each type of exotic matter offers a unique perspective on the universe's workings, hinting at hidden structures and forces that defy conventional explanations. Let's delve further into these tantalizing possibilities. Antimatter and the universe's beginnings. Antimatter, in particular, holds profound implications for the story of the universe's origin. According to the Big Bang Theory, matter and antimatter were created in equal amounts during the universe's earliest moments. Yet, for reasons still unknown, the observable universe is overwhelmingly composed of matter, with antimatter almost entirely absent. This imbalance, known as baryon asymmetry, is one of the most perplexing questions in cosmology. Scientists hypothesize that certain subtle differences in the behavior of matter and antimatter, violations of charge parity (CP) symmetry, might explain this disparity. By studying these violations in high-energy experiments, physicists hope to uncover clues about the mechanisms that tip the cosmic scales in favor of matter. Such findings could illuminate the conditions of the early universe, providing a clearer picture of how galaxies, stars, and planets came to exist. Beyond cosmology, antimatter also challenges our understanding of time reversal symmetry, a principle suggesting that physical laws should work the same whether time flows forward or backward. If antimatter behaves differently under time reversal, it could hint at deeper asymmetries in the universe, perhaps even offering insights into the nature of time itself. Strange matter and the limits of density. Strange matter, too, invites profound questions about the universe's extremes. Composed of strange quarks, this theoretical form of matter is thought to exist at densities far beyond those of ordinary nuclear matter. Its study could revolutionize our understanding of compact objects, such as neutron stars, where gravitational forces compress matter to its ultimate limits. Neutron stars represent a natural laboratory for testing the properties of strange matter. These celestial objects are the remnants of massive stars that have undergone supernova explosions, leaving behind cores so dense that a single teaspoonful would weigh billions of tons. Under such extreme conditions, ordinary protons and neutrons may dissolve into their constituent quarks, creating a soup of up, down, and strange quarks. This state, often referred to as quark-gluon plasma, could provide insights into the behavior of matter under extreme pressures and temperatures. Some theorists suggest that if strange matter forms a stable configuration, it might be able to convert nearby ordinary matter into more strange matter, potentially leading to a catastrophic chain reaction. While this scenario remains speculative, it highlights the importance of carefully studying the properties of strange quarks and their interactions. Understanding strange matter could also have practical applications, such as the development of materials with unprecedented strength and resilience. Axions and the hidden universe. Axions, meanwhile, are perhaps the most enigmatic of all exotic matter candidates. These hypothetical particles, first proposed to resolve the strong CP problem in quantum chromodynamics, could also account for the mysterious dark matter that dominates the universe's mass. Unlike strange matter or antimatter, axions are incredibly light and interact weakly with other particles, making them extraordinarily difficult to detect. Despite these challenges, physicists have devised ingenious methods to search for axions. Experiments such as haloscope searches aim to detect axions by converting them into photons within strong magnetic fields, while helioscope experiments look for axions emitted by the sun. Additionally, axions might leave subtle imprints on the polarization of light traveling through the cosmos, offering another avenue for their detection. If axions are confirmed as dark matter candidates, they could profoundly reshape our understanding of galactic structures and dynamics. Dark matter halos, composed of axions, might provide the scaffolding around which galaxies form and evolve. Moreover, axions could play a role in cosmic phenomena such as galaxy rotation curves, gravitational lensing, and even the behavior of black holes. Theoretical insights and technological frontiers. The study of exotic matter is not confined to theoretical musings or astrophysical observations. It also drives technological innovation, pushing the boundaries of what is possible in particle physics, materials science, and quantum computing. For instance, advancements in particle accelerators have enabled scientists to probe the properties of quarks and gluons, bringing us closer to understanding strange matter. Similarly, developments in cryogenics and superconducting materials are paving the way for more sensitive axion detection experiments. Quantum computing, in particular, stands to benefit from insights into exotic matter. Certain types of exotic particles, such as Majorana fermions, are being explored as building blocks for fault-tolerant quantum computers. These particles, which exhibit unique properties under quantum entanglement, could revolutionize computing by enabling the efficient simulation of complex quantum systems. In the realm of space exploration, exotic matter could serve as the foundation for revolutionary propulsion systems. Antimatter engines, as previously mentioned, offer the promise of unprecedented speeds, while the unique properties of strange matter might enable the construction of spacecraft capable of withstanding extreme environments. Even axions, if harnessed, could lead to new energy sources or innovative communication technologies. Philosophical and existential implications. As we venture deeper into the study of exotic matter, we are confronted not only with scientific questions but also with profound philosophical and existential dilemmas. The existence of antimatter, for example, forces us to reconsider the nature of duality and balance in the universe. Why does the universe favor matter over antimatter? Is this asymmetry a fundamental feature of reality, or merely a consequence of chance? Similarly, the concept of strange matter challenges our perceptions of stability and permanence. If ordinary matter can be transformed into strange matter under the right conditions, what does this say about the nature of reality? Are the structures we take for granted, stars, planets, even ourselves, merely temporary configurations, vulnerable to transformation into something utterly alien? Axions, with their elusive properties, raise questions about the limits of detectability and the nature of the unseen. If these particles pervade the universe, influencing its behavior in subtle yet profound ways, might there be other hidden forces or entities shaping reality? And if so, how can we ever hope to uncover them? These questions remind us that the study of exotic matter is not just about advancing technology or solving scientific puzzles. It is also about exploring the very essence of existence, seeking to understand the universe's deepest truths and our place within it. The philosophical implications of exotic matter resonate far beyond laboratories and observatories, touching on the very core of humanity's quest for knowledge. These questions about the nature of reality and the unseen forces that govern the universe challenge us to expand our perspective, urging us to look beyond the familiar and embrace the unknown. Exotic matter serves as a bridge between the tangible and the theoretical, revealing that there is far more to the cosmos than meets the eye. Antimatter and the nature of symmetry. Antimatter introduces one of the most intriguing and unsettling ideas in modern physics, the concept of symmetry and its potential violations. Nature appears to have a profound preference for balance, but antimatter suggests that this balance can be imperfect. The violation of CP symmetry, the idea that the laws of physics should be the same if particles are replaced with their antiparticles and if time is reversed, hints at deeper asymmetries in the universe. Understanding why antimatter behaves differently than matter is key to answering one of the greatest mysteries. Why does anything exist at all? This imbalance also has implications for the arrow of time, the idea that time has a specific direction. Time, as we experience it, flows forward, from past to future. But if the laws of physics work the same in reverse, why is this the case? Antimatter may hold clues to this mystery. Some theories propose that antimatter behaves as though time flows backward, suggesting that the universe might have a hidden symmetry involving time itself. If this is true, it could change how we think about causality, entropy, and the fundamental structure of the universe. Strange matter and cosmic transformation. Strange matter pushes these philosophical boundaries even further. Unlike antimatter, which mirrors ordinary matter, strange matter exists as a wholly different state of being. The possibility that strange matter could convert ordinary matter into itself introduces unsettling questions about stability and permanence. If strange matter exists and is stable, could it one day transform entire regions of the universe? Could the Earth, under the right conditions, be converted into a strange star? These questions are not just academic. If strange matter is stable, it could mean that our understanding of the universe's structure is incomplete. Stars, planets, and even life itself might be more fragile than we imagine, vulnerable to transformations we cannot yet predict. At the same time, strange matter could unlock new possibilities. Its unique properties might allow for the creation of materials that are incredibly dense, durable, and energy efficient, paving the way for technologies we can scarcely imagine. Axions and the hidden cosmos. Axions represent a different kind of mystery, one that challenges our ability to detect and understand the unseen. These particles are almost ghost-like, interacting so weakly with other forms of matter that they elude direct observation. Yet their very existence could explain some of the universe's most perplexing phenomena, such as the nature of dark matter. The search for axions is a testament to human ingenuity. Scientists have devised experiments that are as creative as they are precise, from using superconducting cavities to detect tiny electromagnetic signals to studying the behavior of stars for subtle hints of axion interactions. These efforts highlight the collaborative and iterative nature of science, where progress often comes from combining diverse approaches and perspectives. But axions also raise questions about the limits of human perception. If such particles exist and play a critical role in the universe, what else might be out there, hidden from view? Could there be other forms of matter or energy that we have not yet conceived of? Axions remind us that the universe is vast and mysterious, full of secrets waiting to be uncovered. Exotic matter and future technologies. The practical applications of exotic matter are as exciting as their theoretical implications. Antimatter, for example, is already being used in positron emission tomography, PET scans, a medical imaging technique that provides detailed views of the body's internal structures. But this is just the beginning. If we can find efficient ways to produce and store antimatter, it could revolutionize energy production and space travel. An antimatter-powered spacecraft could achieve velocities far beyond what is possible with chemical propulsion, opening up the possibility of interstellar exploration. Strange matter, with its incredible density and stability, could lead to breakthroughs in materials science. Imagine constructing buildings, vehicles, or spacecraft with materials that are virtually indestructible, able to withstand extreme conditions without degrading. Such materials could also play a role in creating safer, more efficient reactors for nuclear energy, providing a cleaner alternative to fossil fuels. Axions, though elusive, could have equally transformative effects. If they are indeed the particles behind dark matter, understanding them could allow us to harness new forms of energy, or develop technologies that operate at the quantum level. Axions might also provide insights into the behavior of magnetic fields, with applications ranging from improved communication systems to advanced medical imaging techniques. A universe full of possibilities. Exotic matter challenges us to think beyond the ordinary, offering glimpses of a universe that is far stranger and more complex than we can currently comprehend. Each type of exotic matter, antimatter, strange matter, and axions, adds a layer of depth to our understanding, revealing that the cosmos operates on principles that often defy intuition. These discoveries remind us that science is not just about answering questions but also about asking better ones. As we continue to study exotic matter, we are likely to encounter even more surprises. The universe is a place of endless possibilities, where each discovery opens the door to new mysteries. Exotic matter is a testament to this richness, showing us that there is always more to learn, more to explore, and more to wonder about. The study of exotic matter is not just about understanding the universe. It is about understanding ourselves, our curiosity, our creativity, and our drive to push the boundaries of what is known. These traits have brought us this far, and they will undoubtedly take us even further, revealing new dimensions of reality and inspiring future generations to continue the quest for knowledge. The quest to understand exotic matter doesn't just reveal new scientific knowledge, it reshapes our understanding of reality and the cosmos. These mysterious forms of matter, like antimatter, strange matter, and axions, push the boundaries of what we thought was possible, challenging our intuitions and assumptions. As we dig deeper, the implications of these discoveries begin to touch on the fundamental questions of existence, offering profound insights into the universe's fabric and hinting at untapped potential for future technological advancements. The interplay of exotic matter and cosmology. To truly grasp the significance of exotic matter, we must place it within the broader context of cosmology. The universe we observe today is the result of billions of years of complex interactions involving matter, energy, and fundamental forces. Exotic matter introduces new players into this intricate dance, potentially altering our understanding of how the cosmos evolved and what its ultimate fate might be. Antimatter's role in the early universe. The Big Bang Theory posits that the universe began as an unimaginably hot and dense point. In the first fractions of a second, energy condensed into particles and their antimatter counterparts. This early state was chaotic and unstable, with matter and antimatter annihilating each other in bursts of energy. But somehow, a tiny imbalance emerged. Matter slightly outnumbered antimatter, leading to the universe of stars, galaxies, and planets we see today. This imbalance is one of the great puzzles of cosmology. Why did matter win out? Could exotic particles or processes unknown to current physics be responsible? Experiments at particle accelerators, like the Large Hadron Collider, are probing these questions by recreating conditions similar to those of the early universe. Every new finding brings us closer to understanding why we exist at all. Strange matter and the fate of stars. Strange matter may also play a key role in cosmic evolution, particularly in the life cycles of stars. When massive stars exhaust their nuclear fuel, they collapse under their own gravity, potentially forming neutron stars or black holes. If strange matter exists, it could influence this process in unexpected ways. For instance, some neutron stars might actually be strange stars, composed entirely of strange matter. These exotic objects could have unique properties, such as extreme stability and densities far beyond anything in ordinary matter. Moreover, the existence of strange matter raises questions about the long-term stability of the universe. If strange matter is stable and can convert ordinary matter, could it trigger a chain reaction under the right conditions? While this scenario is purely speculative, it underscores the need to carefully study strange matter's properties and behavior. Axions and dark matter mysteries. Dark matter remains one of the most tantalizing mysteries in modern science. Though we cannot see it directly, we know it exists because of its gravitational effects on galaxies and other large-scale structures. Axions, if they exist, could provide the answer. These particles would have formed in the early universe, spreading throughout space and creating the invisible framework that holds galaxies together. Studying axions could also reveal new information about the universe's initial conditions. For instance, their properties might help explain the formation of cosmic structures, such as galaxy clusters and superclusters. Axions could even shed light on the mysterious phenomenon of cosmic inflation, a period of rapid expansion that occurred just after the Big Bang. Technological implications of exotic matter. The potential applications of exotic matter are as revolutionary as their scientific implications. These materials and particles could enable technologies that seem like science fiction today but may become reality in the future. Antimatter as an energy source. Antimatter holds enormous potential as a source of energy. When matter and antimatter meet, they annihilate each other completely, converting their mass into energy according to Einstein's famous equation. This process is far more efficient than any chemical or nuclear reaction currently known, making antimatter an incredibly dense energy source. However, there are significant challenges to overcome. Producing antimatter requires vast amounts of energy, and storing it safely is even more difficult, as it annihilates on contact with ordinary matter. Despite these obstacles, progress is being made. Advances in magnetic confinement systems, for instance, might one day allow for practical antimatter storage. Such breakthroughs could revolutionize fields like space exploration, enabling spacecraft to travel at unprecedented speeds. Strange matter and advanced materials. Strange matter's incredible density and stability make it an attractive candidate for advanced materials. If we could create and manipulate strange matter, we might develop materials that are virtually indestructible, capable of withstanding extreme heat, pressure, or radiation. These materials could be used to build everything from spacecraft to nuclear reactors, drastically improving their safety and efficiency. Additionally, strange matter might have unique electrical or magnetic properties that could lead to breakthroughs in electronics and quantum computing. Imagine devices that are not only faster and more powerful but also more durable, capable of operating in environments that would destroy current technology. Axions and quantum technology. Axions, though elusive, could have profound implications for quantum technology. Their weak interactions with other particles might allow for the development of ultra-sensitive detectors, capable of picking up faint signals that are currently undetectable. Such detectors could be used in everything from medical imaging to astrophysical observations, opening up new frontiers in both science and technology. Axions could also play a role in quantum computing. If their properties can be harnessed, they might serve as stable, long-lived qubits, the building blocks of quantum computers. This would address one of the biggest challenges in the field, maintaining quantum coherence. By providing a more robust foundation for quantum systems, Axions could accelerate the development of quantum technology, with applications ranging from cryptography to artificial intelligence. Exotic matter and the philosophy of science. The study of exotic matter isn't just about solving scientific puzzles. It's also about challenging how we think. These mysterious substances force us to confront the limits of our knowledge and question assumptions about the universe's nature. What else might we be missing? Are there other forms of matter or energy that we have yet to discover? Exotic matter serves as a reminder that science is an ongoing journey, full of surprises and possibilities. At the same time, these discoveries raise ethical and philosophical questions. If we can harness exotic matter for practical purposes, how should we use it? Should we prioritize energy production, space exploration, or other applications? What risks are we willing to take in the pursuit of progress? These are questions that humanity will need to grapple with as we move forward. A future of endless discovery. Exotic matter represents the cutting edge of scientific exploration, offering glimpses of a universe that is stranger and more wondrous than we ever imagined. As we continue to study these mysterious substances, we are not just uncovering new facts about the cosmos, we are expanding the boundaries of what is possible. The journey is far from over. With each new discovery, we take another step toward understanding the universe's deepest secrets. Exotic matter reminds us that there is always more to learn, more to explore, and more to dream about. And as we push the limits of human knowledge, we can be certain of one thing: the universe will always have more surprises in store. The concept of exotic matter opens up an unending path of wonder, leaving us both awestruck and questioning what lies beyond our current scientific horizons. As we delve deeper, these strange and fascinating substances challenge our understanding of reality and hint at technologies that could redefine the human experience. Unexplored frontiers of exotic matter. Even with the progress made in theoretical and experimental physics, much of the story of exotic matter remains unwritten. Researchers are constantly developing new models and refining old ones to understand the fundamental makeup of the universe. Here are some of the most tantalizing possibilities that remain unexplored. Exotic quark matter. In addition to strange matter, physicists theorize the existence of other forms of exotic quark matter, such as up quark matter and down quark matter. These forms would involve quarks binding in unconventional configurations, creating states of matter unlike anything observed in nature. If these forms exist, they could provide additional insights into quantum chromodynamics, QCD, the theory that describes the strong force holding atomic nuclei together. Studying exotic quark matter could also improve our understanding of neutron stars, potentially helping us identify other unique celestial objects that blur the line between neutron stars, black holes, and other exotic entities. Supersymmetric particles and exotic states. Supersymmetry, SUSY, is a theoretical framework suggesting that every known particle has a heavier superpartner. While SUSY has yet to be confirmed, it predicts particles that could fall under the category of exotic matter. These supersymmetric particles might even contribute to dark matter, offering a parallel to Axions and explaining the mysterious mass that permeates the cosmos. Furthermore, exotic matter could exist in states not predicted by current theories, challenging even the most advanced models of particle physics. The discovery of such states would rewrite the rules of matter, potentially uncovering a shadow universe of particles and forces that interact with ours in subtle and mysterious ways. Interstellar implications of exotic matter. The implications of exotic matter go beyond terrestrial laboratories. They extend into the cosmos, where these strange materials may shape the behavior and evolution of entire galaxies. Consider the following possibilities. Black holes and exotic matter. Black holes are some of the most enigmatic objects in the universe, and exotic matter might play a role in their formation, growth, and interactions. For example, strange matter could accumulate in the cores of black holes, potentially influencing their radiation or stability. Similarly, antimatter could exist in significant quantities around certain black holes, emitting unique signals as it annihilates with ordinary matter. The idea of primordial black holes, formed shortly after the Big Bang, also ties into the study of exotic matter. These ancient objects might harbor clues about the early universe's conditions, including the existence of particles like axions or exotic quark states. Cosmic strings and exotic matter. Another fascinating possibility involves cosmic strings, hypothetical, one-dimensional defects in spacetime that could have formed during the universe's early moments. These strings might trap exotic matter along their lengths, creating regions of intense gravitational and energetic activity. If detected, cosmic strings could provide direct evidence of exotic matter and offer a unique window into the universe's infancy. Exotic matter and galactic collisions. When galaxies collide, the interactions between their stars, gas, and dark matter produce spectacular displays of energy and structure. Exotic matter could add another layer of complexity to these events. For instance, regions rich in axions might exhibit unique gravitational behaviors, influencing the distribution of stars and other matter in ways that defy current models. The quest for exotic matter detection. Detecting exotic matter remains one of the most challenging tasks in physics, requiring cutting-edge technology and creative experimentation. Here are some of the methods scientists are employing or envisioning for the future. Particle accelerators and antimatter production. Particle accelerators like the Large Hadron Collider are critical tools for studying exotic matter. By smashing particles together at nearly the speed of light, these devices recreate the extreme conditions of the early universe, producing fleeting glimpses of particles like antimatter and potentially strange matter. One major goal is to increase antimatter production efficiency. While current methods produce only minuscule amounts, advances in accelerator technology could make antimatter more accessible, paving the way for practical applications. Axion detectors. Detecting axions requires incredibly sensitive equipment capable of picking up their weak interactions with ordinary matter. Instruments like haloscopes and helioscopes are designed for this purpose, using strong magnetic fields to convert axions into detectable photons. As these detectors become more sophisticated, they could confirm axions' existence and unravel their role in dark matter. Astronomical observations. The universe itself serves as a vast laboratory for studying exotic matter. Telescopes and observatories around the world are searching for signals associated with antimatter, axions, and other exotic particles. For instance, gamma-ray telescopes might detect the annihilation of antimatter in space, while gravitational wave detectors could reveal the presence of strange stars or cosmic strings. The ethical and philosophical dimensions. The pursuit of exotic matter also raises profound ethical and philosophical questions. As we unlock the secrets of these substances, we gain the power to manipulate them in ways that could benefit or harm humanity. Consider the following. Environmental impact. The creation and storage of exotic matter may have unforeseen environmental consequences. For example, producing antimatter requires significant energy input, which could strain existing energy resources or contribute to greenhouse gas emissions. Similarly, experiments with strange matter must account for the remote possibility of triggering catastrophic chain reactions. Philosophical implications. Exotic matter challenges our understanding of reality itself. What does it mean to exist in a universe where such substances defy our intuitions about matter and energy? How do these discoveries reshape our place in the cosmos? These questions remind us that science is not just a technical endeavor, it is a deeply human pursuit, driven by curiosity and wonder. A vision for the future. The study of exotic matter is still in its infancy, but its potential is boundless. As we continue to explore these strange and unknown forms of matter, we are likely to encounter new mysteries, each more fascinating than the last. From unlocking the secrets of the universe's origins to developing technologies that transform society, the journey promises to be as rewarding as it is challenging. In the end, exotic matter represents more than just a scientific curiosity. It is a testament to humanity's insatiable desire to understand the world around us. By pushing the boundaries of knowledge, we not only discover the universe's hidden truths but also redefine what it means to be human. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.